And now I'm recording. Yes. Let me do this.
So I need to share my screen?
Yes.
Okay. Did you see my screen?
Yes, we can see our screen.
Okay. Okay. Good morning, gentlemen. I think I'm going to make something like a 40 or 45 minutes presentation. And what I'm going to present really is a combination, at least 2 or 3 papers that we introduced to the industry almost 3 or 4 years ago, and we're still working on this issue for a long time. So, and the title is really a little bit challenging, and what I'm trying to show here is try to question the issue that in some cases really the induced fracture complexity is not really totally necessary in conventional reservoirs. So my main focus is going to be unconventional reservoirs. So if you work in a different topic, I think that you are going to really try to learn something new. If not, at least you can see some really good practical topics that you can use actually, or you can use later. So normally when we were talking about unconventional reservoirs, there is really a general, really well accepted hypothesis that the induced fracture complexity, in addition to the primary hydraulic fracture, is a key component for maximizing hydrocarbon recovery in unconventional reservoirs. This is really the common accepted hypothesis in the unconventional reservoirs industry. But in reality, what I'm trying to show here is this is not really totally necessary in all the unconventional reservoirs. And if I show you this cartoon and make a question regarding to the type of fracture geometry you are going to prefer, especially when you're dealing in unconventional reservoirs, let me use my pointer. So if I show you this type of fracture geometry, this is the wellbore and the perforation cluster of this black symbols here, and this one are the fractures. So if I show you this type of fracture in unconventional reservoir and also this one, I think everybody is going to try to really easily to understand, to answer the question that they are going to prefer more this type of complex fracture geometry and conventional. And this is really one of the things that we always accept, that especially in unconventional reservoir where the permeability is very low, so we're going to prefer this type of fracture geometry. But in reality, as I'm going to show you later, that in the real world, we don't have any way to control this type of complex fracture geometry. There is one alternative in the industry that, and this is really what the industry is trying to use, is that using the slick water or low viscosity fracturing fluid, and assuming that we are really fracturing really formations with easy frackability, and we are going to be able to get this type of fracture geometry or complex fracture. But in reality, in most of the cases, we're always going to get this type of planar fractures in all the cases. And to show you that this is really the case, if you see before, there is really many papers discussing the hydraulic fracturing test site result from Wolfcamp formation and Midland Basin. So you can see that in many cases that the fracture is really, for example, like showing here, this is a core sample. This is the natural fracture, and this is the hydraulic fracture. So we can see that in the real world that in reality, in many cases, the hydraulic fracture is not really following the natural fracture plane. It's really bypassing that or creating an angle. If we try to really correlate this with the real world, it's easy for us if we have a formation with natural fractures. The fracture is always going to follow the natural fracture planes, but this is not really the real case. And the other really important observation from here is that natural fractures or the hydraulic fractures could be really mainly planar. And the distance between the fractures could be really close, like I'm showing here. So, and if we go back to the theory that, especially if we go back to the theory that the geomechanics is going to play a big role in, especially in the fracture generation and also in the interference between the fractures, we are not going to be able to explain this type of planar fractures very close each other. So it means that in reality, in the downhole, the fracture is really following mainly planar planes, or are really planar. This is also an important observation from the real world. This is also the same case for the hydraulic fracture test site in the same formation where here we're showing, this is the wellbore where they're using the two perforation clusters. So this is one cluster, the brown one is one cluster with 3 perforation clusters, and this one is the second cluster. So this one is the fracture wellbore, and this red one, this is the core sample they were able to recover from the formation close to the fracture formation. So you can see here that the red one is the core sample. The red one is the hydraulic fractures. There is a really huge number of hydraulic fractures in the core, in the recovered core, and also you can see that according to the calculation they made in the previous publications, so for 2 clusters of perforation with perforation clusters, they did that. The spacing between the perforation cluster was 2.5, and they use 6 shots per foot. And if you use 2 clusters of perforations, and the distance between the stage length is almost 200 feet, so it means that you are going to assume that you're generating 1 fracture per perforation. So in theory, in 400 feet of wellbore, you are always only going to be able to generate 90 fractures, assuming that you are generating 1 fracture per perforation process. So it means that when you are going to try to recover a core sample like this one, we only need to be able to see at least 90 fractures. But in reality, what the lab observed after analyzing detail the core sample, they get almost 324 hydraulic fractures in the 400 feet. So it means that in downhole, there is really a lot more fractures that we're generating when you are trying to really stimulate the formation. So this is really, but the good observation from this core sample is that most or many of the generated fractures are really parallel to each other. There is not really a classical complex behavior like I showed before. So this is only the introduction. So in this presentation, what I'm going to try to show you is that it is, in some cases, really very difficult to find out the correlation between the production and the fracture surface area. So, and for these cases, it is really normal to make really a combination between the surface area generated by the fracture and also the formation properties. So, especially if we are really stimulating very well an unconventional formation, the production behavior is mainly related to the unconventional reservoir permeability and also to the fracture complexity. So the fracture complexity and also the permeability has really a good correlation. What we did in one of the SP papers we presented some time ago is that, especially, we are trying to show that to the industry that the complexity is really important just in some specific cases. So to do that, what we did was to use the two cases, the unconventional gas and unconventional liquid producer reservoirs, where for the wide range of permeabilities changing from 10 nanodarcies to 1,000 nanodarcies, and also considering the stimulation efficiencies, we were able to get with some really good observation that in some cases the fracture complexity is not really totally necessary. Before to go to really to show you the details of the result, so really when is the fracture complexity really totally necessary, it's really important for us to be sure that we are really optimizing the fracture spacing to be able to get really a good, meaningful information of the requirement of the fracture complexity in any unconventional reservoir. So for that, we did the fracture spacing optimization, and this was presented in the SP paper 163833. And what we are trying to really show with this paper was mainly especially to try to optimize the number of fractures per well and also the horizontal well spacing. This is really two important parameters, especially when we are dealing with unconventional reservoirs, because in unconventional reservoirs, especially in North America and also outside of North America, the completion cost, especially for unconventional, is really very, very important. And this is really more important for North America, where the gas price is really very low and where it is really totally necessary to optimize the number of fractures or the horizontal well spacing, especially to try to be really at least in some economic margins, especially for North America. This is not really totally true for outside of North America, because in outside of North America, the gas price is really totally different. And so it means that in theory that outside of North America, the companies are not really totally, or that the stimulation process is not really totally dictated by the price of the gas. So how was our process to try to really to optimize the fracture spacing and also the lateral well spacing? So we know that, especially if you guys are working reservoir simulation, if we have all the reservoir details of the permeabilities, rock properties, we have the PVT or fluid properties, and we have the details of the fracturing stimulation we're planning, and we're going to be able to set up a really good reservoir simulation, and also when doing that, we're going to be able to make a good study to try to see which options could be really the best the best one, especially from the recovery point of view, and also from the economic point of view to try to optimize the fractures or the stimulation in any unconventional reservoir. So using the reservoir simulators, we're going to be able to include, for example, if we like the stress effect on the proppant, we're going to be able to include the stress effect in the rock or the permeability or porosity. We can consider a multi-phase flow or non-Darcy flow, etc., depending on if we have more information, we can try to use that in the reservoir simulation. But unfortunately, especially if we're working in reservoir simulation and in unconventional reservoirs, we're going to spend really some time trying to set up the model, and also we are not going to be able to really produce really a good information from the stimulation, because always we're going to be missing most of the information I'm listing here, especially if we're going to use the simulation for unconventional reservoirs. In unconventional reservoirs, for example, considering the size of the reservoir, or also talking just from the one wellbore, we are going to deal with for example, if we're dealing, for example, with 10,000 feet of horizontal section, and we're making at least 60 or 100 stages per well, so it means our simulation is going to be really very, very complex. So it means that our simulation time is really going to be time consuming and also labor intense. So, and as I mentioned before, unfortunately, especially we're dealing with in unconventional reservoirs, we are not going to be able to have all of this information from the start. So it means that we're going to miss many informations for our simulation. We are always going to lack especially to have really good simulation results, at least to try to recommend to our field people what could be the best strategy to stimulate the well. So based on that, so what we did in the SP paper 1638-33 is to try to work or use something we call as a back of the envelope practical methodology to try to optimize the stimulation process just using the available information from the conventional reservoir. So I'm talking here, so just knowing the reservoir permeability and the fluid properties for gas or liquid, I'm talking in this case for oil, we are going to be able to develop really a simple correlation to try to optimize to try to really to calculate what could be the optimum fracture spacing. And I'm going to show you later this correlation. So what we are showing here is mainly, especially for very complex reservoirs like conventional reservoirs, just knowing for gas or liquid producer and conventional reservoir, just knowing the permeability and also the viscosity of the fluid, we can calculate the optimum fracture spacing. To come out with a back of the envelope correlation. So what we did that we make some really a lot simulations. For that, if this is the well and we're generating really transfer fractures, and the theory behind the transfer fracture, especially for unconventional reservoirs, the best stimulation option, especially for this type of reservoir, is to generate a transfer fracture. So, the reason for that is because normally we're going to place the horizontal wellbore parallel to the minimum stress. So it means that any fracturing that we're going to try to generate is going to be really transferred. So if we're generating transverse fractures like I'm showing here, so for our simulation, what we are doing is isolating just one fracture like here. And this is going to be our simulation model to optimize at least the fracture spacing for our simulation. So what I'm showing here is that this is the horizontal wellbore, my fractures, and the drainage area per fracture is going to be really very well known, especially for unconventional. If we're working with unconventional reservoirs, the fracture is not going to be able to drain farther than the fracture tip. So my upper and lower limit for my reservoir size or the drainage area for the fracture is going to be the tip of the fracture. And for in the other side, the other limit for my drainage area per fracture is going to be the midpoint of the distance between the fracture spacing. So knowing that, so we know that for the simulation, we're going to know the volume of the drainage area per fracture. So knowing the volume of the drainage area per fracture, we're going to be able to optimize really the number of fractures to try to recover or maximize the recovery. So for our simulation in gas cases, we're assuming that we're going to be able to drain at least 80% of the gas in a period of 30 years. So we use this type of information to try to, and also the PVT of the gas or PVT for liquid. We use also the relative permeability for both fluids. And using that, we are going to be able to really run many simulations for cases like here. So we changed the permeability of formation for gas and oil from 1 to 1,000 nanoounces. And we changed the conductivities from fracture conductivities. I'm talking about proppant conductivities from 1 to 100 milliards feet. And also we consider changes in the fracture spacing from 500 feet to 2,000 feet. So we try to really use a wide spectrum for the permeability, fracture conductivity, and wall spacing. In addition to that, to be able to consider the property of the fluid, and this I'm talking here about the gas and also the oil. So we also use different values for the reservoir pressures, changing from 3,000 psi to 10,000 psi, and also the changing the temperature, reservoir temperature from 150 degrees to 300 Fahrenheit degrees. So changing the permeability, the fracture conductivity, the well spacing, and also the fluid properties, we were able to come up with this type of simple correlation. So you can, if you have time, you can try to review in more detail the SP paper. I'm showing the 163833, or you can also check this paper. So you can see all the details how we came out with this type of correlation. So you can see, especially here, to optimize the fracture spacing. This is for gas and this is for liquid. So for gas, to optimize the ideal fracture spacing in a conventional gas producer reservoirs, we only need to know the permeability of the formation, the drawdown, and also the gas viscosity. So if we know these three parameters, and mainly the permeability and also the viscosity of the gas, we are going to be able to calculate this parameter, and using this parameter, we can come out here. For example, if this ratio is 6, I can easily calculate the ideal fracture spacing of 300 feet. So I don't need to really know more parameters of this to make an easy calculation of the fracture spacing for my a specific project. And this is, the red one is for gas, but the green one is for oil. So for the case of oil, we only need to also to know the permeability of the formation and also the viscosity of the oil. And permeability divided by the viscosity is really mobility. And so we know that the mobility and the square root of mobility of the for liquid, for hydrocarbon, is going to give you the value to try to use this correlation. So knowing the square root of the mobility for oil, we're going to be able to easily calculate the fracture spacing, the ideal fracture spacing. When I mentioned here the ideal fracture spacing, I'm not really considering any correction regarding to the stress effect on permeability and regarding to the stress effect on the fracture conductivity. I'm not using or making any correction regarding to the fracture complexity or any other parameters. So this is the ideal fracture spacing. But in the real world, we need to consider this type of correction. So, and to do that, we also run more simulations. Just to show you some examples. For example, like here I'm showing the effect of the proppant distribution or proppant settling, especially in the fracture spacing or recovery factors. You can see here that especially for the cases where the proppant settling is really important, and this is totally true for unconventional reservoir where we're using very low viscosity fracturing fluid like a slick water. So we're going to see that there is really a big effect of the coats effect, because the proppant is really more heavier than the slick water, and it means that when we're going to use slick water for fracturing and we're trying to place proppant in the formation, it means that the proppant is always going to try to settle easily in the fracture. So it means that especially when we're using the very low viscosity fracturing fluids, the proppant is always going to be located very near to the wellbores. So to be able to push the proppant farther from the wellbore, we need to use really more viscous fracture fluid, but this is not really the option, especially for unconventional reservoirs. So we can see here that if we have the residual permeability above if this is the fracture and where we have the proppant settling and the total fracture is this one, it means that above the proppant bed, we have some type of residual permeability or conductivity, like I'm showing here, is 0.01 milliamps. The proppant settling is only going to be really very important for low permeability reservoirs. But if you have really permeability higher in the range of 10 to 100 nanometers permeabilities, the proppant settling or the residual conductivity is not going to be really totally important. But if we have the normal case where we don't have any residual permeability above or conductivity above the packet fracture, so it means that the effect of the proppant setting is really going to be really totally important. So based on the simulation, what we're showing here, depending on the effective fracture height ratio, and we are using this picture, we're going to be able to correct, for example, the effect of the proppant setting, especially in the fracture spacing. For example, if we know that the ratio between the generated fracture or packet fracture and the generated fracture is 0.5. So it means that we're packing the 50% of the fracture height. It means that the fracture spacing needs to be corrected at least for 35 or 40% of the ideal fracture spacing we're calculating with the previous correlation. Another example of that, really another case where we're also showing here is that the fracture conductivity is also really affected by the closure stress, especially in the case of the deeper unconventional reservoir where the stresses are really very high. And also since the industry is really using a low quality proppants like a natural sand, it means that the stress effect is going to be really totally important, especially for unconventional reservoirs. So we're showing here that if we don't consider the stress effect, our fracture spacing, for example, for 109 hours of permeability could be 100 feet. But if we consider the stress effect, this one is with no stress, so could be 200 feet. But if we consider the stress effect, we are going to at least to lose we need at least to correct by 50% the fracture spacing. So it means that the stress effect in the fracture conductivity is going to play a big role, especially in unconventional reservoirs. And the other really important parameter, especially to optimize the fracture spacing, is also the stress effect on the permeability and porosity of formation. So for our case, we only did a study for the stress effect on the permeability. And what we are showing here, considering this typical effect on the stresses for permeability, so we're showing here that especially for unconventional reservoirs, it will be necessary at least to make something like the 50% of correction of the fracture spacing to be able to minimize the effect of the stresses, especially in the recovery factor in gas producer reservoirs or oil producer reservoirs or liquid producer reservoirs. It means, for example, if my ideal fracture spacing for gas producer reservoir is, for example, 50 feet, considering the stress effect on the reservoir permeability, we need to apply the 50% of correction. That means that our calculated fracture spacing needs to be 50 feet instead of 100 feet. I'm going to escape this one. So based on what we're showing here, the fracture spacing is really important, especially for unconventional reservoirs. So we were able to present to the industry really a very simple correlation to calculate the optimum fracture spacing in unconventional gas producer reservoir or unconventional liquid or oil producer reservoirs. So especially for gas or liquid producer reservoirs, we only need to know the mobility of the gas or mobility of oil and apply the correlation to try to calculate the optimum ideal fracture spacing. And after that, we can apply the corrections I showed before to try to assure that we are really placing the proper fracture spacing, especially in unconventional reservoir. So again, this back of the envelope fracture spacing calculation is only valid for formations with permeability not higher than 1,009 ounces. If you are dealing with formation with permeability higher than 1,009 ounces permeability, this correction is not applicable. This is mainly due because if your permeability is really higher than 1,009 ounces, there is no way for us to justify that you are not really draining the reservoir farther than fracture tip. That's the main justification to reuse this type of constraint for our correlations. So it's our maximum permeability for this type of correlation is 1,009 units. So again, the idea, the correlation is going to only give you the initially the optimum, sorry, the ideal fracture spacing, but the ideal fracture spacing needs to be corrected by the fracture complexity. It needs to be corrected by the stress effect on the fracture conductivity, the stress effect on the permeability, and also the settling effect of the probe. So depending on the type of condition that or technique you're applying in the field, you need to correct the ideal fracture spacing to be able to assure that you're really stimulating very well the formation. So once we did the fracture spacing optimization, now we need to talk about the fracture complexity. So and this was really one of the topics of this presentation. Fracture complexity is really important or not in unconventional reservoirs. So to do that, like we did that before, and to optimize the fracture spacing, what we are doing here is, again, we are isolating one fracture here. So this section is here. So my wellbore is this blue point. My fracture is this one. Well, to try to consider the complexity of the fracture, I'm placing, so we are placing the transverse complexities here. With that, we are trying to consider especially the complexity of the fracture. So if this one, for example, the fracture length is, the fracture length is 240 feet, and we're considering complexities of 40 feet. So this is really to try to mimic the effect of the complexity on the fracture, hydraulic fractions. So it means that for this type of fractures, we're using the fracture conductivity is going to be generated by primarily by the fracture, but the fracture complexity here, we're assuming that the fracture complexity conductivity is 1 milliards feet. 1 milliards feet for the fracture complexity is really good value, because remember that the conductivity of the formation, if we try to calculate based on the permeability of formation and the thickness, is going to be really much lower. So with the contrast we're creating between the flow capacity of the formation and the complexity conductivity is really huge. So 1 milliards feet of conductivity for the complexity is really much higher than the formation flow capacity. So we're really creating good contrast. So to make the study that if the fracture complexity is really important for all the cases, so we also did some really we also really use a big window, especially for reservoir permeability. Again, we are using the same window for reservoir permeability from 10 nanodarcies to 1,000 nanodarcies. The fracture half length was limited for our simulation to 240 feet. So it means that if we're using the 240 feet of fracture length, it means our fracture spacing needs to be 480, the lateral wear spacing needs to be 480 feet. But just to try to avoid any type of problems in the simulation, we consider that the lateral spacing is 500 feet. So it means that the fracture length is 200 feet. So we're leaving at least 10 feet of space between the without fracture to avoid any type of problems in the simulation. And as I mentioned before, the complexity, this is the complexity. So we're changing the length of the complexity from 120 feet to 1,600 feet. So we're using the a small number of complexity and also very high number of complexities to try to see what really could be the effect of the number or the value of the complexity in the recovery factor. And additionally, we use a terminology what we call as a complexity ratio. The complexity ratio in this case is going to be the ratio between the total length of the branches, so the total length of these branches compared with the fracture length. And we're changing here from 0.25 to 3.33. So we're using a wide range for the complexity ratios. For our fracture simulation, we use this type of tapered fracture conductivity. And we're using this type of geometry in the simulation for that. And also that, in addition to that, one important parameter, especially to try to consider really, is especially for productivity and also for recovery factor in the conventional, is what we call as or the industry is calling the stimulation efficiency. The stimulation efficiency in this case is mainly related to like I'm showing here, if we have a stage with 3 clusters of perforations, if we are going to be able to generate 1 fracture per perforation, we're going to be able to drain the entire connected unconventional area for productivity. But in reality, the generation of the stimulation efficiency of 1 is not really common in the industry. So in most of the cases, we're going to be able to see this type of stimulation efficiency of 0.5. It means that we're going, if we're placing 3 clusters of perforation or 4 clusters of perforation, we're going to only be able to generate 2 fractures, for example. And the other 2 is, we're not going to be able to fracture. So it means that we're only going to be able to drain a portion of a 50% of the connected unconventional area to the wellbore. And this is the area the worst case where, for example, if we place a 3 cluster perforation, we're just generating 1 fracture per cluster. It means that we are draining the entire connected area with only with 1 fracture. So it means that our condition to really to get the higher recovery factor is going to be really worse, because especially in conventional reservoirs where the permeability is very, very low. So it is really a good alternative or good option for us to try to get this one. So we need to try to get the stimulation efficiency of 1 or be able to generate 1 fracture per perforation cluster, at least to be able to maximize the recovery. So using these criteria, we were able to make some real, also another simple back of the envelope correlations to try to see that what would be the effect of the complexity, especially for a conventional reservoir. This is generating only planar fractures, and this one is generating the complex fracture or complexity. So it means that, especially if we're generating only planar fractures, we're going to be able to estimate the recovery factor based on time, stimulation efficiency, and also permeability. So we know the time is one parameter where we know that depending for how long we like to read to make the study, we can try to see what is going to be our recovery factor based on the stimulation efficiency. So if we know that the classical stimulation efficiency for the industry, I think is in the optimum case could be 0.75. It means that we can use this parameter, and if we know the permeabilities, we are going to be able to calculate or estimate the recovery factor for our well assuming that we're only generating planar fracture. But if we generating some degree of complexity, we can also calculate the additional recovery factor where we can get just really by the complexity we're generating in gas, or for the case of oil, we're also going to be able to make the same calculation. But the main objective of this paper was not really to try to show this really back of the envelope correlation. Our main objective on the paper was to demonstrate to the industry when is really important the fracture complexity, especially for gas or oil producer reservoir or liquid producer reservoir. So, and for that, you can see that we ran many simulations for different permeabilities from 10 nanoanalysis to 1,000 nanoanalysis. So you can see, for example, here for 10 nanoanalysis, and we are using here different fracture complexity ratios. So it's 0.25 up to 3.3. So if you recall, the fracture complexity ratio is the ratio between the length of the complexity divided by the length of the fracture. And it means that, especially for gas reservoirs, the fracture complexity is only important, you see here, up to 100 nanoanalysis. Above 100 nanoanalysis, the fracture complexity is not really totally important. So what does this mean? If we are dealing with formation with more than 100 nanoanalysis, we don't need to really to assure that we are generating complexity in the fracture. So, and to be able to do that, it means that especially for gas producer reservoirs, it's not totally necessary to use slick water to stimulate the unconventional reservoir. Remember that to be able to, the industry, what is using actually to try to generate complex fracture in downhole is using low viscosity fracture fluid. But if the permeability of formation is lower than, is higher than 100 nanometers, it means that we don't need always to use the slick water. So it means that we can use a different type of fluid system to try to generate a more optimum fracture. So again, for gas reservoir permeabilities or for gas reservoirs or unconventional gas producer reservoirs, the fracture complexity is only necessary for permeabilities lower than 100 nanometers. Above that, we don't need to assure that we're to generate complex fracture. But for the case of liquid producer reservoirs, the simulation is showing that the reservoir permeability, especially for liquid producer reservoir, needs to be lower than 500 nanoanalysis. If you see here, especially the complexity of the fractures is really important between 10 or 50 nanoanalysis for liquid producers. Above than that, the complexity is not really adding too much to it. But just to consider that if we fix that, for example, if we get more than 2.5% of recovery increase, it means that for liquid producer reservoirs above 500 nanoanalysis is not really important to have complexity in liquid producer reservoirs. And the reason for that is especially for liquid producer unconventional reservoirs, to be able to extract hydrocarbon from the formation, we always need to have higher permeability than the case of gas. So as a conclusion of this study, so I think I mentioned many times that especially for gas producer reservoirs, it is really important, the complexity is really important, especially for formations below 190 ounces for gas and 590 ounces for oil producer reservoir. This means that especially if you're dealing with gas producers unconventional or liquid producer unconventional, normally the fracture spacing, the optimum fracture spacing for a liquid producer reservoir needs to be at least 50% of the calculated fracture spacing for gas producer reservoir. So this, for sure, this conclusions regarding to the optimum fracture spacing are not really based on the economics. So with the in the paper we didn't consider the economic sorry. Yes, and then I quit. So especially for formations with a really with higher conductivity, we don't need really to assure that the complexity of it means that achieving the complex fracture is not really critical, especially for high permeability liquid or gas producer formations. So, and finally, I think that one of the really key issues, especially in unconventional reservoirs, is the stimulation fluid, sorry, the stimulation efficiency. The stimulation efficiency is really important, especially if we're dealing with unconventional reservoir where the formation permeability is very low. So at any means, we need to assure that really higher values for stimulation efficiency. Like for example, idea it could be good to get one or at least something close to one to be able to minimize the effect of the permeability and also the effect of the complexity of geomechanics, especially in conventional reservoir. With that, I think that I finished my presentation. I'm really happy to answer any questions if you guys have something. And
yeah, thank you so much, Leopoldo, for the presentation. It was really informative. We have some questions here in the chat. So Oscar is asking for hydrofracturing design, which is the best analytical equation to describe stress shadow effect. He says that he is using Snowden and Warpinski and Tufels. He is asking which one is better to use in order to estimate the stress shadow effect.
Yeah, it depends from the simulation tool we are using. I use a lot of Gopher software, and the Gopher software is using the Snell.
Okay, so Oscar, it's Snowden that Leopoldo is using mainly, but you can explore the other simulation tools that to answer your question. We have Malkov. He's asking, he's congratulating you first for the excellent presentation, and he's asking if you could mention the type of fluid and support agent used to optimize spacing on the fracture influence the simulation. The fluid type and support agent used to optimize the spacing of the fracture in the simulation.
Yeah, and remember, especially in the interesting is using the slick water to stimulate the unconventional risk. So, slick water is really low viscosity fracturing fluids. In some cases, some people is using linear general. In some cases, they are using water with friction reducer. So the final viscosity of fluid is still very low. So we are using this type of fluid for our simulation. But what we are suggesting in the presentation is based on the permeability of the formation. We we don't always really need to use always slick water. We can use really higher viscosity fracture and fluid, especially we're dealing with higher permeability and conventional reservoir. But especially due to the cost issues, especially for North America, I think nobody's actually, they're going to try to switch to higher viscosity fracture and fluid because the cost is going to be more higher, and the economics is going to be really a big role in, especially moving or changing the fracture and fluid. So that's the reason why we're always using slick water for our study.
I have a question regarding the optimization technique that you have suggested in your paper. You have assumed that all the fracture have the same length or the same geometry. So how can we correct the optimization technique to accommodate to the part where we don't have the same fracture height in stimulation?
Well, that's a good point. So remember that unconventional reservoir are really very complex environment.
Yes.
Also that there is no way for us to, especially for example, for conventional reservoir to consider all the changes in parameters. So as I mentioned in the presentation, this is only really a back of the envelope approach to try to make some types of really easy correlations, especially to help the small companies, because if you're dealing with very big companies like, for example, Shell, I think they can have some time really more time or more information to try to read, to at least to use simulations to try to get to release some little bit more better result. But especially for small companies where they don't have too much information, this correlation could be really helpful. But anyway, that changes in the fracture length or fracture height is really common in the industry. So the unique way to try to consider that is assuming that you have all the information, you can set up a real reasonable model to try to see that what could be really the effect of these changes in these parameters, especially after the well is fractured, and you can try to see that. Especially making something like a corrosion history matching to try to see what could be the effect. But at this stage, I think our unique option is only to use the same fracture length for all the fracture. I think many people or many software are using the same approach, and also the same fracture heights.
I see. So like in the beginning of your presentation, you have talked about but sometimes we do not stimulate the natural network, the natural fracture network. So how can we like explain the high productivity? Sorry. How can we explain the high productivity that we have from unconventional, even though we have very low permeability, since we don't intersect some of these natural fractures?
Yeah, and that's a good point. So in some cases, I think that in some cases the fracture is really fill it up with with calcite, and
Yes.
depending, especially depending the angle, how the fracture is propagating regarding to the angle of the fault.
Yes.
In some cases, you are going to really preferential, the fracture is going to cross the fault. So it depends mainly from the angles, but also from the mineralization effect and the natural fracture. That's main. But in theory, that if you have really an open fracture or a weak fracture, and the hydraulic fracture is going to really to prefer to follow the plane of the natural fracture instead of crossing.
Another question is like in conventional reservoir stimulation, we start by pumping 100 mesh proppant in order to propagate into the natural fracture. Was that is this theory is proven by simulation, or it is only a theory that the natural fractures are going to be propped with the 100 mesh?
That's really good question. In reality, we try to make the summary real observations from what really we get in the downhole, and also the size of the 100 mesh proppant is really bigger than the width of the natural fractures.
Yes.
Any proppant or proppant size bigger than the natural fracture width, there is no way for us to place 100 mesh, especially in the natural fracture. So that's the reason why I think that we introduced to the industry that what we call as a micro proppant is almost a 325 mesh high strength proppant.
Yes.
And the micro proppant has some options to try to go inside the natural fracture. So we're really packing in some way the natural fracture. So that's really the selling point for micro proppant. But 100 mesh is not really is really bigger than the width of the fracture, the natural fracture. So we're not going to be able to place the 100 mesh. The 100 mesh mainly is used especially to wash out or to remove the stress effect around the wellbore, especially the stress gauge in the wellbore, especially in the perforations. This is one. Or in some cases also we're using the 100 mesh especially as a diversion system to try to block some to divert the proppant from one plane to another plane. So
I see. So
but it's not going to be mainly to the natural fractures.
So it is more of like a friction to the fracture surface in order to make it smoother and make sure the proppant is going inside.
So if I try to go back to I think that we're showing that here. So let me show you again. So this one. So if you see here,
yes.
Do you see my pointer?
Yes.
So they're showing a picture of where the proppant concentration is very big here. So there is it's like the fracture was totally packed with proppant, 100 mesh proppant. So, but here the problem here is that the concentration of the proppant is very high. So it means that the proppant was really, the concentration was really magnified here by the breaching effect. It's not really the typical packet proppant. So if we're packing the proppant, normally proppant, the concentration of proppant needs to be really smaller than this one. So.
I see. Another question that I have is like if we use the conventional simulators like the Gopher or the STEM plan, we are going to get like almost similar results to the very sophisticated simulators in terms of fracture geometry. Like there is not that much difference.
No, remember that the fracture simulator are really different depending on the theory behind
yes.
that. So Gopher is really Gopher or STEM plan there. You can get the different geometries. It depends from especially for example, I know very well Gopher, and in Gopher you're going to be able to estimate very well at least the vertical stress profile distribution. But if you have a really good vertical stress distribution calculation, you are going to have really more chances to make a better simulation, at least to the vertical fracture growth.
I see.
And in a STEM plan, you can have some. It's going to be really a little bit different. So it's like, for example, with fracture is really more more easy way, really more easy to use in the field. But in reality, the fracture geometry you are going to get, fracture is going to be really totally different. It depends from the simulation and also
Leopoldo,
the theory behind it.
Leopoldo, I have a question. Yeah, related to this. Okay, that you say that those simulators can help us. As you know, that so for example, if we want to develop some new exploration fields, Luna formation, Muerto formation, you know, in our countries, that when we don't have, we don't know the whole properties of those reservoirs, what is the best option to develop a new exploration wells in terms of hydraulic fracturing?
Yeah, but anyway, in exploration, you're always going to have access to the log information. So if you are logging, at least you're running at least a good suite of logging tools, like for example, Sonic or triple combo. So using this information, the Sonic and also the triple combo, you're going to be able to at least to generate a good stress profile for your well bore. So I think you still have tools to try to estimate these parameters. But the unique thing you are going to miss, especially if you're calculating your parameters for fracture design from logs, is you need to at least to calibrate that could be just using something like a defeat or could be the microfrac, depends on which one you are going to be able to use in the field. And calibrating with that, your logs, you are going to have a very good way to estimate the vertical stress profile, and with that you can use any software. This is also valid for exploration.
Yeah, that's true. Okay, thank you, Leopoldo.
Leopoldo, if we have like a horizontal stress difference, is it going to influence our fracture geometry? Like in the same layer that we are trying to fracture, there is difference between the minimum and the maximum stress. Is this going to influence the geometry or the net pressure of our hydraulic fracture?
That's a good question, though. So the difference between the stresses in the horizontal plane is going to really play a big role, especially in a convention. So in theory, it's much better that this difference could be really minimum in a conventional reservoir, because if the difference is really very low, it means that we're going to be able to generate really complex fractures in the well, in the formation. But if the difference is higher than, for example, more than 250 feet or more than that, it means that the fractures is always going to follow one plane. So that's really one of the key points. Normally, when we're drilling a conventional reservoir, we're always going to try to know the difference between the minimum and maximum stress, and based on that, we're going to be able to see that we're going to be able to generate a really complex fracture or just planar fracture. So that's the theory behind that. And you know, since you're working in soft formation, that normally the difference between these two parameters is going to be very, very low.
Yes, I was studying, I was simulating this part, and I found that if the difference increases, we are going to have more net pressure.
Yeah. The net pressure is going to be one of the indicators for that.
We have another question from Malkov. He said, in your presentation, you showed the graph of stimulation efficiency. The information for this analysis was get through production log or in the design of smart wells with fiber optics?
Okay. The stimulation efficiency here is only referred to the generated fracture per cluster. So say if I have two perforations in the stage, if I fraction the formation, I generated two fractures, it means that my stimulation efficiency is 1. But if I only generate one fracture, it means my stimulation efficiency is 50%. Nothing to do with the productivity as well. It's mainly the number of fractures I'm generating per stage. And this is really one of the key points, especially in convention, because as I mentioned, that if you are not going to be able to generate a stimulation efficiency close to 1, it means that you are generating one fracture per perforation cluster. It means that you are missing some connectivity between the fractures and the reservoir. So it means that your recovery factor is going to be lower.
Yes, Malkov is from Lima, Peru. This is what he's saying. He's in Lima, Peru.
Okay.
Yeah, so with this, we have, I think, covered all the questions that we got from the audience and the questions we have. If anyone have any questions, he may speak up now. Otherwise, we have reached the end of our webinar for today. So, Leopoldo, if you have anything to say, we would be more than happy to hear about that. And if anyone have any question, we would be happy to cover them.
No, I like only to say thanks for your invitation. I'm really open for any other request, so I can. Now I have more time than before that. I'm really working in my own company, so if you
Nice.
like any other help, I'm really free to do that. So thanks for everybody attending this meeting. And if you guys like the copy of the papers or you like the copy of the presentation, just send me an email so I can forward to you. So
yes, thank you so much, Leopoldo.
Okay.
We really appreciate your time. Thank you, our audience, for attending today's presentation, and we all have a good day. Thank you.
Thank you.
Bye.
Thank you, Leopoldo.
Bye bye.
Bye-bye.
Bye-bye.